Section 7.2 in your book is titled Estimating a Population Proportion. And basically what we're going to do in this section is, if we're given some kind of a large population, all right, let's say that this is a population of people, we want to come up with some kind of a proportion. The number of people that like chocolate ice cream, or the proportion of people, or the percentage of people that are Republican, or something like that. And this proportion of the population is denoted with the small letter p, the lowercase p. So lowercase p, again, that represents the population proportion. And what we're going to try and do is we're going to try and come up with some kind of an estimate of what the actual proportion is of some population given a sample. And that's what we're after. We're going to look at a sample, analyze it, and say, we think the actual proportion of the population is this. And when we do that, we're going to introduce in this section, and more importantly the entire chapter, the idea of a confidence interval. And that is, we're going to say something with a certain amount of confidence. We're going to say that we think the population proportion is this with a certain amount of confidence. So let's look at an example. Let's say that we are going to look at, we'd like to know the proportion of lefties by taking a sample. All right, we take a sample. Let's say our sample size is 30. Let's say we take 30 people. We can pick 30 people from the school, or just take a sample of 30. And when we take that sample of 30, we find out that 4 of them are actually lefties. So in our sample, our proportion in our sample, and remember, we denote that by p hat. The p hat is our symbol for a sample proportion. So in this case, the proportion of lefties in our sample is just the number we have out of our sample size, or 4 out of 30. And if we reduce 4 out of 30 or take it to decimal, we get a p hat of 0.0133. That would be our sample proportion. Now the other thing that we can say here is, if our proportion of lefties is, 0.0133, we call this a point estimate. Point estimate. And oftentimes that point estimate, it might be a good point estimate, it might be a bad point estimate. It might have been that in our sample size of 30, 15 of them, by some odd chance, ended up being left-handed, and then our p hat would be 0.5, which we probably can use common sense and know that we wouldn't say half of the population is left-handed. So this point estimate, like I said, can be either good or it can be bad. So what we want to do with this point estimate is try and build some kind of a confidence interval that says, well, we can say with about 95% confidence, or 90% confidence, or 99% confidence that the actual population proportion would lie in this range. And that's what we're going to work on in this section, is coming up with a confidence interval. So what does it mean by saying we have a confidence interval? Well, first of all, let's kind of define what a confidence interval is. So we can say a confidence interval is a range of values used to estimate the true value of a population proportion, which is called a parameter because it's not a statistic because it's not part of a sample. It's a parameter because it's part of an entire population. In a confidence interval, sometimes we abbreviate it with just CI. If you see CI, we're talking about a confidence. And along with confidence intervals, we also sometimes use the phrase a confidence level. And usually we use 3 common confidence levels. We'll use 90%, we'll use 95%, and we'll use 99%. Those are the 3 that we see the most often. Now that doesn't mean we couldn't build a confidence interval that has a confidence level of 85%. But when we start getting below 90, then what we're really doing is saying we're not real confident that the actual population parameter, the population proportion, is going to fall within that interval. So we tend to use 90, 95, and 99 the most. Now here's a really important thing about confidence intervals, and it's how we interpret the confidence interval. So we have to interpret it correctly. What is it we're trying to say? So let's say we're looking at the 95% confidence interval. So we take our sample and we get our p-hat, and then we build this interval in which we think that our actual population proportion, our p, will fall. So here's the correct way of saying it. The correct way would be to say that once we build the interval, and we'll do that here in a second, that we would be 95% confident that that interval actually contains the true value of the population proportion p. What that means is if we were to select many different samples of size 30, like we did with the lefties, and construct the corresponding confidence intervals, 95% of them would actually contain the value of the population proportion, which means 5% of them wouldn't. That takes into account some of those bad point estimates that we might get, where we get 0 out of 30 people that are left-handed, or we get 15 out of 30 people. What is wrong to say, it would be incorrect to say that there would be a 95% chance that the true value of p falls within that interval. All right, there's a subtle difference there. The correct thing would be saying we are 95% confident that p falls in that interval, not that there's a 95% chance that p would fall in that interval. And as we do an example, you'll see that. All right, to build our confidence interval, we have to have what we call some kind of a margin of error. We use capital E to denote that. So I'll write that down. That is our margin of error. And that margin of error is going to be based upon our sample size, what our random variable x is, as well as how big we want this confidence interval to be. So what we say is that the actual value of p is going to fall between our p hat, our sample proportion, minus our margin of error, and our p hat plus our margin of error. So we're saying we get this p hat, and we're going to add our margin of error and subtract it, and then somewhere within this interval, we're going to say our value of p is going to lie in here, in between there. And that interval, depending on the confidence interval we use, is going to be either bigger or smaller. So let's say that, I know we've been talking 90% or 95%, but let's say that we used a 99% confidence interval. So if we were going to say that we were 99% confident that our p-value laid within this interval, then our interval is actually going to be a little wider. All right, so the higher our confidence interval, then the wider the interval is going to be. So if we decided we wanted a 90% confidence interval, we're not quite as sure, so we leave a little more room for error, our interval will actually be narrower. So the higher the number, then the wider our confidence interval will be, because we're more confident that it lies within this interval. So how are we going to build that interval? All right, let's take a look at that. Let's go back to our example of lefties. Okay, so we took a sample size of 30, and we found that there were 4 lefties in that sample size of 30. So our p hat value was our 0.133. In other words, that was 4 out of 30. So what we want to do is, we want to decide what is our margin of error. So for this problem, what we're going to say is we're going to build a 95% confidence interval. So we need to find that margin of error that is associated with these numbers of n equals 30, x equals 4, and our p hat of 0.133. To help us build those confidence intervals, we're going to use a website, and I've put it on the Edmodo page so that you don't have to type in that big, long website. And so you can get to it from the Edmodo page. And what it is it's a statistical calculator in which we are going to enter sample size, the observed proportion, and then we get to pick the confidence level we want. So let's go ahead and enter a sample size of 30. So if we enter a sample size of 30, it's not going to let me do it. There we go. If we enter a sample size of 30, and we enter the observed proportion. Now notice it wants the observed proportion as a percentage. So the 0.133 is actually 13.3%. And we're going to select our desired confidence level of 95. And if I hit calculate, it gives me a confidence interval of plus or minus 12.15. Now that's a big spread. So it's saying that the true proportion is within 12.15% above 13.3 and 12.15% above. And if you notice at the bottom, it says the range for the true population proportion is 1.15% to 25.45%. So in this problem, our margin of error, it said was 12.15%. And if we put that into a decimal, that's going to be 0.1215. So here's our p hat, 0.133, and I'm going to add to it 0.1215 to get the top of my interval. I'm going to subtract 0.1215 to get the bottom of my interval. And that's where we get the numbers that were given to us in the calculator, that if we add the two, 5, 4, 5, 2, that's going to be the top of our interval. The bottom of our interval, 5, 1, 1, 0, is the bottom. So we're going to say with 95% confidence, I'm going to slide over this way, with 95% confidence that our interval is going to be between 0.115 and 0.2545. It's a pretty wide interval. There's a couple reasons why. One, we used a 95% confidence interval. If we wanted it to be a smaller one, then we'd use a lower confidence interval. And if we wanted, and one of the reasons why it's so big is our sample size. Our sample size was only 30. That's a very small sample if we're trying to find out something about an entire population. So the bigger the sample size, then that's going to affect the interval in which we're working with. So let's try an example. Let's say that we have a sample size of 1,236. Now that could be people or whatever. Let's just use people. And we have 109 of them that meet our criteria. So let's say that they like butterscotch ice cream. So our p hat, that's going to be our sample proportion, is just going to be our random variable x divided by the sample size. So that would be 109 divided by my n value, 1236. Let me punch that in the calculator here real quick. And my p hat is 0.088. That's my p hat value. So what I'm going to do is build a confidence interval. Let's say on this one, we want a 99% confidence interval. That means it's going to be a fairly wide interval. But remember, our n was pretty big, 1,236. So the true population proportion is going to lie between our p hat plus our margin of error and our p hat minus our margin of error. And to find that margin of error, I'm going to go to that website. I'm not going to put it on here, but I'll do the calculations off to the side. And when I run those calculations in that website, it gives me a margin of error of plus or minus 2.08. Now remember, that's in percent. So what we're going to have to do in order to figure the top is take our p hat and add our margin of error, which in this case becomes 0.0208. And we're going to take our 0.088 and we're going to subtract our margin of error of 0.0208. And if we do those calculations, and I'm going to take some liberties with this because I'm also haven't have the website up, that the true population proportion given this sample size of 1236, given our random variable of 109 and using a 99% confidence interval, we can say we are 99% confident that the true population proportion will lie between 0.672 and 0.1088, or in percentages, be 6.72% and 10.88%. Now, in your book, there's a lot of formulas they give you for finding those confidence intervals. That's why it's going to be important that you bookmark on your tablet this calculator. And again, it's on Edmodo. You can find the calculator on there, and then you can bookmark it on your tablet so that you have it. So one more example before we turn you loose on your homework. And I'm going to look at number 32 in your book. It's on page 341. It's not one of them that I've assigned to you for homework, but it's definitely one that would be an example of what we'd expect you to do. And the problem says an important issue facing Americans is a large number of medical malpractice lawsuits because they're very expensive. So in a study of 1,228 randomly selected malpractice lawsuits, it was found that 856 of them were dropped. So 856 of the 1,228 were dropped or dismissed. The question says, what is the best point estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed? So the best point estimate is going to be that p hat. So in our problem, our p hat is going to be 856 out of 1,228 of the lawsuits are dismissed or later dropped, meaning they just go away. So the proportion on that one, our p hat would be 0.697. So almost 70% of the medical malpractice suits are dropped or dismissed. So this number would be our best point estimate. Now, if we only took 20 lawsuits and just evaluated those 20, we probably wouldn't get as good of a point estimate. We could, but chances are we're not going to get a great point estimate. But if we look at over 1,000 of them, then we're probably going to get a pretty good point estimate. The second part of the problem says to construct a 99% confidence interval, 99% confidence interval estimate of the proportion of malpractice lawsuits that are dropped or dismissed. So we're going to take our point estimate of 0.697, and we are going to then find our margin of error. That's what we'll do in our calculator. So we'll find our margin of error, and we'll add it to 0.697, and we'll subtract it from 0.697. So if we go to our technology, and I've punched the numbers into the calculator where I use 1228 for n, and I use, remember we put it in the calculator, we put it in as a percent. So when I put it in the calculator, I'm going to put in 69.7% in for our p hat, or our observed proportion. And I selected a confidence interval of 99%. I get a confidence interval, or an E, our margin of error, of 3.38. Now remember, that's in percent. So if I put it back into a decimal, I'm going to take 0.697 and add 0.0338, and I'm going to take 0.697 and subtract 0.038. So our confidence interval now becomes that the true population proportion is going to fall between 0.6632 and 0.7308. And again, that's the .697 plus this, the .697 minus our margin of error. And you notice it was one more decimal. And again, I'm using the results from the calculator that it tells me at the bottom of the page. Excuse me. So the last part of this problem says, does it appear that the majority of such suits are dropped or dismissed? Well, what does it take for it to be a majority? For it to be a majority, then we need to say that more than 50% of the lawsuits are dismissed or dropped. And we're saying with 99% confidence that the actual proportion of suits that are dropped falls between 66.3% and 73.1%. So are the majority of cases or lawsuits dropped? Yes. We can say with 99% confidence that the majority of these malpractice lawsuits are dropped. And again, that was an example of number 32 on page 341 in your book.